In this video, we're going to be talking about the Earth's magnetic field. Now, the magnetic field of the Earth is believed to be due to the presence of an imaginary bar magnet. An imaginary bar magnet, okay, situated at the center of the Earth and inclined at a small angle to the Earth's axis of rotation. Now, diagrammatically, this is what it looks like. We have figure 1 being the Earth's imaginary bar magnet situated at the center, okay, situated at the center and inclined at a small angle to the Earth's axis of rotation. Alright, so due to this bar magnet, this imaginary bar magnet, we have a magnetic field formed around the Earth. Alright, this is what our magnetic field looks like. We have the lines of force starting from the North Pole and ending at the South Pole. Alright, as you can see here also. So this is what the Earth's magnetic field basically looks like. So the Earth has a magnetic field, and the magnetic field of the Earth is due to an imaginary bar magnet situated at the center of the Earth and inclined at a small angle of rotation, at a small angle to the Earth's axis of rotation. Alright, so this is the Earth's magnetic field. Now, the next thing we're going to be talking about is a bar magnet in the Earth's magnetic field. How would a bar magnet, alright, placed in the Earth's magnetic field behave? This is the Earth's magnetic field, as you can see here. If we put a bar magnet in the Earth's magnetic field, how is it going to act? That is what we are going to be looking at in these two sessions. Now, there are two ways we can place this bar magnet. We can place this bar magnet with south pole pointing upwards. We can also place it with south pole pointing downwards, as you can see here. Alright, for the first example, we have bar magnet placed with south pole pointing upwards or pointing north. South pole pointing upwards and north pole pointing downwards. And then the second illustration here, we have bar magnet with north pole pointing upwards and south pole pointing downwards. All right, so what is going to be the result of this? Now, do not forget the Earth has a magnetic field, and the magnetic field of the Earth has north pole down and south pole up. All right, so we have the lines of force coming from north pole going to south pole. This is the Earth's magnetic field. These outer lines of forces here are the Earth's magnetic field. All right, that's what we have here, the Earth's magnetic field. And then these ones we have here, these inner ones here, are the magnetic field of the bar magnet. Now, like I said earlier, the north pole of the Earth's magnetic field is down, all right, or in the southern hemisphere rather. The north pole of the Earth's magnetic field is located down, all right, or we can say in the southern hemisphere. All right, now if we have north pole and north pole directly opposite to each other, what we're going to have is a repulsion, and that's the result we have here. All right, now we have this bar magnet with south pole pointing upwards or pointing north. Now do not forget the south pole of the imaginary bar magnet of the Earth is located in the southern hemisphere. So we have south pole and south pole, all right? So we're going to have repulsion. So because we have north-north repulsion, south-south repulsion, we're going to be having repulsion in these 2 points. And then this space here is what we call neutral points. That repulsion will give rise to what we call neutral points. Now the neutral points are points where the Earth's magnetic field completely neutralizes the field due to the bar magnet. Now, the net magnetic force at such points is usually zero. So take note, the magnetic force at these points is zero because they are neutral points. Neutral points are basically points where there's no magnetic force. Okay, so if we place a bar magnet in the Earth's magnetic field, a bar magnet with south pole pointing upwards and then with south pole pointing northwards and north pole pointing southwards, we're going to have the neutral point like this. All right. Now, this is another case of a bar magnet with south pole, all right, pointing downwards and north pole pointing upwards. Now, do not forget, we have the Earth's magnetic field, all right, located outwards, and then we have the magnetic field of the bar magnet. Now, also, as you can see here, the north pole of the imaginary bar magnet of the Earth is located in the southern hemisphere, as you can see here. All right, it's located in the southern hemisphere. We have north pole down, then we have the south pole up. Now, in this case, we have the south pole pointing towards the northern hemisphere. So we have south and south from the bar magnet, and then north pole from the imaginary bar magnet of the Earth. So in that case, we're going to be having north and south. In that case, we're going to be having an attractive force. So this is what we have here. And then for the one up, we're going to have attractive force again because we have the south pole of the imaginary bar magnet and the north pole of the bar magnet placed in the Earth's magnetic field. So in that case, we're still going to be having north and south, and that will give us an attraction. But then you discover that as we move further away, all right, the attraction from the Earth's magnetic field, all right, the attraction between the Earth's magnetic field and the bar magnet placed in the Earth's magnetic field will decrease, all right, because we'll be moving further away from the magnetic field of the bar magnet. So as it decreases, we are going to have neutral points formed. Okay, so moving further away, we discover that that attraction will be decreasing. As the attraction is decreasing, attraction between the north pole of the Earth's magnetic field and the south pole of the bar magnet is decreasing. We're going to be having attraction between the north pole of the Earth's magnetic field and the south pole of the Earth's magnetic field increasing. All right. So in that case, we're going to be having neutral points, okay, formed horizontally as we have here. All right. Do not forget the neutral points are points where there is no magnetic force. Okay. So this is what we have here. So this is what the neutral point looks like for a case where we have a bar magnet with south pole pointing northwards and north pole pointing south, with south pole pointing towards the south and the north pole pointing towards the north. And then this is a case for bar magnet with south pole pointing towards the north and north pole pointing towards the south. Now the next thing we're going to be talking about is the angle of dip and the angle of declination. The angle of dip is also known as angle of inclination. Now before we talk about that, we need to talk about two very important terms, which are the geographical meridian and the magnetic meridian. And the geographical meridian is a line that carries the north pole and south pole of the Earth. You can see it here. This line here, okay, this line here is our geographical meridian. We have the north pole and we have the south pole. All right, the straight line that carries both north pole and south pole is what we call the geographical meridian. Now we also have the magnetic meridian. The magnetic meridian is a line that passes through the axis of a freely suspended bar magnet. All right, don't forget, if we tie a bar magnet at the center, all right, we talked about this in the introduction to magnetism. If you've not watched that video, make sure you go back and take a look at it. Now, in that video, we said if we tie a magnet at the center, all right, and we suspend it freely, it will oscillate and then come to rest in a north-south position. All right, now the magnetic meridian is a line that passes through the axis of a freely suspended bar magnet. This is what we have here. All right, magnetic meridian. Now, when we talk about angle of declination, it's simply the angle between the geographic meridian and magnetic meridian. Don't forget, geographic meridian carries north pole and south pole of the Earth. All right, so the angle formed between The geographic meridian and the magnetic meridian is what we call angle of declination. The angle of declination is the angle between geographic meridian and magnetic meridian. And then we also have the angle of inclination, which is also known as the angle of dip. This is the angle between which the axis of a freely suspended bar magnet makes with the horizontal. Alright, so we have the axis of a freely suspended bar magnet, and then we have our horizontal. Let's say our equator here is our horizontal. So the angle formed between the axis of a freely suspended bar magnet, alright, and the horizontal, okay, is what we call the angle of inclination. So we can say this is our angle of inclination here. Okay, this is our angle of inclination. The angle between the axis of a freely suspended bar magnet and the horizontal.